Okay, so to introduce the problem, I want to just very briefly begin by just recalling the classical Collamore-Lumberry problem, which will then be extended to incorporate a problem with investments. So the original Collamore-Lumberry problem was introduced already in 1903 by Lumberry as a model for an insurance company which simply gains capital from premiums and loses capital from claims. And in Lumberry's original model, okay, yeah. In Lumberry's original model, it's assumed that the payments are made to the insurance company, which arrive at a constant rate, so that's the constant C. And then there are claims losses, which arise at a Poisson rate according to a size psi sub I, which is assumed to be IID. So in other words, this is an example of a Lévy process, which usually is assumed to have positive drift. And then the Rouen problem asks the following question. If we assume that the initial capital of the company starts at a positive value U, then what is the probability that the process is ever negative? And then in a classical result of Collamore, it's known that as in an asymptotic sense, if we let the initial capital U tend to infinity, then this probability decays at a certain exponential rate, so according to a constant C times e to the minus RU. Okay, so in this talk, I'm going to be interested in an extension of this model where we assume that the insurance company invests its excess capital. So we'll start with the same model as on the previous slide, except that everything that I will discuss will now be in discrete time. So we'll be looking at the increments of the company, say from time n-1 to n. And this discrete increment will be denoted by L sub n or minus L sub n. So L sub n will be the losses of the insurance business that occur during the nth discrete time interval. Okay, next we're going to adjoin an investment process, which means that at any given discrete time, we assume that the insurance company invests the excess capital and that this earns returns on the investment, which are denoted here by R sub n. So this will be assumed to be an IID sequence. And this leads us to now the recursive, a recursive sequence of equations which describe the capital of the company at a given time. So we start again with a fixed capital U. And then if we want to compute the capital at time n, this is obtained by taking the previous capital, multiplying this by the investment returns, and subtracting the losses from the insurance business. Okay. First of all, I want to quickly remark that, that from an analytical point of view, the solution to this problem is also well known. To describe the solution, it's helpful to introduce what's I'll call the cumulative discounted loss process, which essentially sums the losses of the insurance company from time 1 to time n, except that if we look at a loss that occurs at, say, time n in the future, this is now discounted according to the inverse of the investment returns that accumulate from time 1 to time n, or n-1. And so this is now a process which is shown here in the picture. It now starts at 0. It decays along the negative axis. And of course, there's now a lot of dependency in the step sizes which come from the discounted returns. But nonetheless, one can easily show that if we would like to study the probability of ruin in the case of investments, which is the probability that the process y is less than 0 for some n, then this can be likened to the probability that the discounted loss process exceeds a positive barrier at u. So we're led to this boundary crossing problem, which is illustrated on the right-hand side. We now have a discounted loss process here, and in order to determine the probability of ruin, this means that we need to understand the probability that this process is larger than a positive barrier at u. So in other words, that means that we need to understand the behavior of the supremum of the process script L sub n. To do this, it's most convenient to observe that this process satisfies a random recurrence equation. So that means that that to understand the random variable script L, we can write this as being equal in distribution to a function of the unknown random variable script L. So in other words, we have a special case of the general equation where we have a random variable z, which is unknown, which is equal in distribution to a function phi of z, where phi is a known random function of the unknown variable z. And in this general framework, we can appeal to a very general result of Goldie from 1991, which discusses solutions to recurrence equations of this type. And so in his case, he makes some additional assumptions on the form of the function phi of z, which says in a very rough sense that this should look like a multiplicative factor a plus a kind of error term. And this, in fact, can be verified. These conditions can be verified in the context of the Ruin problem. And so we end up with the asymptotic result, which says that the probability that the random variable z, which in our case would be the supremum of the loss random variable, the probability that this is larger than u, decays like a constant c times u to the minus r. And actually, Goldie gives also a very nice characterization of this decay rate, the factor r appearing in this equation. This comes from looking at the cumulant generating function of the multiplicative factor a. So in other words, the generating function of log a defined here. This has 2 zeros, and the non-trivial 0 is the solution to where this function is 0 is in fact the rate of decay appearing in this formula. So if we translate this result into the Ruin context, then we can identify the multiplicative factor a as just being the discounted returns on the investments. So this leads to the conclusion that the Ruin probability decays at a polynomial rate rather than an exponential rate, and that the decay rate is determined by the investment process. So in other words, the random variable d, which relates to the returns on the investment. In this expression, the constant c is, of course, much more complicated to determine, but in some special settings, this is where our contribution comes in. One can actually, for example, in this context and some other general settings of this type, one can also obtain an explicit representation for the constant, which would naturally involve both the insurance business and the investment returns. But from the point of view of this talk, we can concentrate on just the asymptotic form, which says that the decay rate is decaying in some sense in a large deviations. In the sense of large deviations, there's a rate of decay, and the rate of decay in this context is determined by the investment returns. Okay, so what I would like to focus on this talk will be important sampling methods for this problem. So I'll start with the same problem that was introduced on the earlier slide. So we're again studying an insurance company with investments, and the total capital is denoted by y sub n, which satisfies a certain recursive sequence of equations. We're interested in studying the probability of ruin, which is the probability that the process y sub t is ever less than 0. And then, as I already noted, this decays according to a certain polynomial rate. Okay. From the importance sampling perspective, the question that we would like to address is to obtain an exact numerical method for estimating this small probability. From this formula, we can immediately see that this is a rare event probability as it decays to 0, and this suggests that a natural candidate for estimating the probability would be through importance sampling. On the other hand, in contrast to a classical Ruin problem, the random variable y sub n is actually highly dependent. So the step size involve the investment returns in a multiplicative way. So there's a certain dependency that arises. And if one were to apply importance sampling in a naive way in this problem, one essentially sees that the variance of the estimator blows up compared to the estimator. So in some sense, you don't get efficiency in that way. So to get around this, so in some sense what we would like to observe is that we have a kind of large deviations problem. But if we want to apply importance sampling to this problem, we would want the process that we are trying to estimate to look something like a random walk. But if we focus on the loss process, which one studies for the theoretical solution, the loss process manifestly does not have this kind of random walk representation, so we need to take another approach. And so to get around this problem, we look not at the process, the risk process itself, but rather at the dual process. So in particular, what we would like to look at is not the problem of estimating the ruin probability directly, but rather of estimating an equivalent problem which involves the tail exceedances of a associated content process. So this leads us to the idea of Sigmund duality, although here we're actually following another version which is from Asmussen and Sigmund. And in the general form, this allows us to equate, for example, a ruin probability of a risk process with a tail exceedance probability of a content process. So in the general formulation, we would start with, say, a stationary driving sequence, call it U sub n, and a content process V sub n having this general form. And then it's possible to associate a risk process Y sub n, which is related by taking, where the functions g and f are related by being inverses of one another, and where in the risk process, the stationary sequence runs backwards in time rather than forwards in time. Okay, and then the sort of fundamental lemma that I will need in this talk is the following lemma, which appears both in Sigmund and the later paper Asmussen and Sigmund, which says that if we would like to study the ruin probability for a risk process, this is equivalent to the steady state probability of an exceedance for the associated content process. And this is illustrated here in the picture. We have a particular risk process which is actually drifting to infinity, and we relate that to an associated content process where we would like to study the steady state exceedance probability of that process. And the simplest example of this would be, for example, in just this case of a single server queue, where one can equate the exceedance probability in steady state to the probability of ruin of a classical Collamore-Lumberry process. But in our context, of course, the risk process is different, and so it's not immediately clear, for example, what is the relevant content process that appears in this duality lemma. Okay, so in our case, we have a specific risk process, which is shown here at the top of the slide. And in that case, one can actually compute the content process, which has the form shown here as the function, as the sequence V sub n, which is related to the original risk process by means of where the random variable A has the distribution of the inverse of the investment returns. And then once again, we can study the ruin probability by studying the exceedance probabilities of the associated content process in steady state. And it's actually, in some sense, interesting to observe that the content process is actually also a process that occurs rather widely in other contexts in applied probability, so it's not merely a theoretical object. For example, one context where it arises naturally is in the context of financial time series modeling, where one is interested in studying, for example, the squared volatility of a Garch 1-1 process. And in that case, the squared volatility actually solves exactly this equation. And there are other examples also, for example, in branching, where similar equations arise. So no matter how we wish to interpret the content process, we nonetheless are led to this equivalence. And so then the objective will be to study the simulation problem not for the original risk process, but rather for the associated content process. And at this stage, it's perhaps interesting to understand why the content process would be somehow more natural to simulate using rare event simulation than the original risk process. Well, in both cases, the processes are Markov chains, but in the case of the content process, the random variable A is related to the random variable R sub n by being an inverse of this. And so that means that actually V sub n is recurrent. It recurs to 0. It has an atom at 0. So therefore, we can study the exceedance probabilities by studying cycles of the Markov chain which return to 0. So this is the approach, which is that we study not the original process Y sub n, but rather the dual process. And then because the dual process is a Markov chain which recurs to 0, so it has an atom at 0, that means that we can relate the steady state exceedance probability to by means of a representation formula which says that the probability that the content process is larger than u can be related to the expected exceedances above u during a cycle of the Markov chain which starts at 0 and then ends at 0. So if we look at the cycle of a Markov chain starting at 0 and returning to 0, then a typical cycle might look like this. So there will be under a typical cycle, we would never reach the high level u. So the event that we exceed the high level u is a rare event, and so this is what we would like to simulate. So to simulate this quantity, okay, so first of all, we observe that this is then a rare event, and so this suggests that we can estimate this rare event by means of a large deviations change of measure. And for this purpose, it's helpful to introduce a particular change of measure which we actually encountered in the theoretical, when we studied a theoretical version of this article, where we look at, again, where we focus on the 0 point of the random variable log A and introduce a change of measure according to this shift. This is done randomly until the level u is attained, and then we revert back to the original measure. So in some sense, it's a dual change of measure where we change the measure according to a natural shift up until the level u is attained, and then we revert back to the original measure until the regeneration cycle is complete. In other words, until the Markov chain returns to 0. And the motivation for writing it in this form can be seen by just the observation that as we're estimating an event where the process V sub n is getting large, and as V sub n tends to infinity, the first two terms in this expression dominate over the last term, and so in some very rough sense, this begins to look like a random walk, and that suggests, at least in a very rough sense, that this should be an efficient algorithm. So to show that this is efficient in a mathematical sense, then we need to first of all have a way of relating the quantity that we're trying to estimate, the n sub u, compared with the same quantity in the shifted measure. So we have this representation formula here, which then identifies an estimator for the quantity n sub u, which is unbiased. And then the main result says that for this estimator, one can actually show that we have bounded relative error. And that also, if we compare the estimator compared with other estimators having different changes of measure, we can in some sense show that this change of measure is optimal in the sense that any other change of measure has cannot have bounded relative error or logarithmic efficiency. Here's just a simulation study for this process applied to a ruin problem. And in this case, we can see that that the relative error is actually well controlled even in the extreme, where we take a very large value of u. And so in some sense, this shows that the algorithm works very well in the standard settings where one has, for example, a risk process or a ruin problem in the setting that I introduced at the beginning. Okay, I'll finish by just saying a couple words about some extensions that we're thinking about. So one question that you could perhaps ask is under what circumstance, so the algorithm is very general. It doesn't really even assume that the mean drift of the insurance business is, for example, positive. But one could ask under what circumstances would the algorithm be in some sense slow to converge to the so that the relative error is still bounded, but where the constant is very large. And some insight into that can be seen by this example, which is that in some cases, which would generally be the cases where you would have, for example, the loss process would be positive rather than negative, one has a very long return time. One could have many returns to values close to zero before a large exceedance takes place. In this case, one also needs to pay attention to the regeneration times of the underlying Markov chain, and that plays an important role in the estimate. So in this context, it becomes interesting to also consider state dependence in the sense that the behavior near zero is in some sense away from the large deviations regime, and so it makes sense to consider alternative changes of measure in this region, which is something we're looking at. And another extension that we're looking at is in the direction of statistical samples, where we might have, where we work with the empirical distributions rather than the actual distributions. And at least the original simulation studies show that this works well, but we hope to show that this also in a more theoretical sense. Okay, so this is part of a series of papers which have been dealing with more generally nonlinear renewal theory for perpetuities. And in this particular talk, which is the second, is based on the second article in this series, I've specialized this to the setting of ruin with investments and the important sampling problem for this. Okay, thank you.
So we are running a bit late, so we should try to keep those questions and answers short.
So just one observation, I think, is one of the advantages of using important sampling for estimate ruin probabilities is that you actually can estimate anything that is conditioned on ruin, like the overshoot, because the important sampling constructs the path, the whole sample path on the set of ruin. You actually can estimate not only the ruin probability, but the conditional overshoot at the time of ruin, so that type of thing. But one thing is that, isn't it true that by passing to the duality, you have lost that here? Because the process is not the same anymore. It's okay for the steady state and the heating time. That identity is true, but the process is not true for the whole process.
Yeah, I agree that in the sense of duality, once you pass the dual process, you lose something.
That aspect, right?
So the probability of ruin is equivalent, but
in the middle,
but going beyond this is a more delicate game. So
and also you have also when you do this type of representation for heavy tail problems, which at the end this is a heavy tail problem because the tail is Pareto, is not. What happens is that you need to assume like finite variance or something of the. Don't you need to assume something about that? That the Kramer, something that the standard, the asymptotics only assume that there is a Kramer root for the discount, right? But don't you need to assume something that there is more, like that you need beyond that thing? Your algorithm seems to.
There are no assumptions other than assumptions. Well, okay, the precise assumptions are here.
Two times R.
Yes, and then there's another assumption which I didn't state explicitly, which is an assumption on the return times to zero, essentially. That's here, but this can always be avoided by passing to the K chain rather than to the chain itself. So this is no problem in practice.
Okay, thanks once more.